Are you all able to see the screen?
Yes, Honorable.
Yeah, it's a day two now. Uh, okay. Mm. So for today's session, first I will just recap it. So last session we have learned about how to give a input file for the silicon, and we have done an SCF calculations. We have done total energy calculations. This was our first job for our last session. So what we have done, Amazon sampling with K points, and we have taken different amount of K points to see variation of total energy is. And with increasing, we find a optimized value for the K points. We have find optimized value for the cutoff energy. So with the optimized value, today we'll start next calculations. Means after total energy, what we can do from these things, from this um, quantum ESPRESSO. So first, we'll discuss about the band structure calculation. What is a band structure? The band structure is a representation of allowed energy levels. Sorry. So to do the band structure calculation, first we need to find what is its prevalence. Because no, if we calculate the properties in the first zone, then we can find the properties of the system as a whole. So for band structure, we need to go along a particular direction. Like I have shown it here. It's a the black line. I'm here just considering the black line. It may be the black line should be at any direction, whatever interest for you. So unlike this whole Brillouin sampling, we just now need to take the K points along this particular direction. So what we need to know, we need to know what is the direction we want to calculate the band structure. Secondly, we need to know what is the initial point of this line, what is the final point of this line. If we know these things, then we will be able to calculate structure along this particular path. So what we need to do for this thing, we first need to do self-consistent calculation, SCF calculation, then we need to do bands calculation, and after that we need to do post-processing. Means data we got from the band structure calculation, we need to make it, we need to arrange it in a proper way so that we can plot it out. So from here, what we need to know? We need to know the direction. We need to know the points where the symmetry line starts or and the end point. Now come the also of a silicon, of silicon, bulk silicon. So you can find, you can pull it up, will give it, you can use X Christian software to find the symmetry points. So what we are seeing it here, it has symmetry points, gamma point, L point, U point, it's just a name, X point, and for every point, it has a location in the reciprocal space. The symmetry points, we can say this is the symmetry points. We can say gamma is the symmetry points This is at 0, 0, 0 position. X is the symmetry point 0, half, half position. L point is a half, half, half position. You don't need to worry about what are the points. You can find it out very easily in literature or in X crystal. You can find it out what are the positions of the system. Here I have taken from this website, and from this website also you can find the points. So in quantum ESPRESSO, we have to give these symmetry points in a particular fashion. What we need to write in the K points card, write as a crystal B coordinate system. After that, you need to give how many points you want to take. As here, I am trying to calculate the band structure along this L to gamma to X to gamma direction. So I have taken 4 points. So I have written it here 4. And after that, along the sequence, what I want to take as a output, I have put it up the points. I have put it up L points, gamma points, X point, and again gamma points. Now another point, another number, I have put it up as after this 40. 40 means if I want to go from L to gamma, we need to take 40 points. You can say it 60, you can say it 80, that depends on you. Means here to here along the black line, if I start from here to here, I am saying the code that you divide it in 40 points. I need to take the data point. I need to take actually 40 data points along the line. So you can change it up. More you put, it will take more time, but the curvature will be more appropriate for you. It is the number. So it depends on you how you want to calculate this. Okay, the same thing also below here. So now, next, just I am showing what I have changed for this silicon SCF, because I told you that first I did SCF calculation, then bands calculation. So for this is the input file of SCF, you know the SCF files. Now in the band file, what I have changed it up from the calculation, but you are able to see it.
অরুণাভদা
Yeah?
অরুণাভদা তোমার কথাগুলো না মাঝে মাঝে কেটে যাচ্ছে, শোনা যাচ্ছে না। ইন্টারনেটের প্রবলেম হচ্ছে মনে হচ্ছে।
হ্যাঁ, ইন্টারনেটের প্রবলেম হতে পারে। Now you are able to hear me?
হ্যাঁ, এখন শোনা যাচ্ছে। তুমি তোমার ভিডিওটা অফ করে দিতে পারবে? তাহলে হয়তো ইন্টারনেট একটু মানে অডিওটা বেটার হতো হয়তো।
Yeah, I've stopped my video. Now you are able to see my screen.
Yes, yes.
You are able to hear me?
একটা কিছু নোটিফিকেশন, ঠিক আছে ঠিক আছে।
Okay. Okay. This is a comparison between the SCF file and the bands file. So what I have changed the calculation from SCF to bands, and the K point part I have changed from this automatic to crystal big. But so you have to do these two things change. But here you need to remember that prefix and outdit should be same for the SCF and bands calculation. So this is an exercise. You can do it in the exercise. So no problem. On in file where this is a sample input file where you need to fix the prefix and outdit same. Here, what it will do? It will create a bands.dat file, data file. What you have calculated with the band structure, it will stored as a data file. And in the next run, what we will find from this data file, it will generate a plotting file. Means it's a 2-column data file. It will be bands.xmgr file. Here, one thing you should notice that the output is showing the highest and lowest level for the occupied states. So you can find Fermi energy from here. You can put anything because Fermi energy is a reference level. I have put it just the Fermi energy in between these two numbers. So during plotting, you can do this. So I have written it up in the exercise file. So you can plot it out. Okay. This is the output file. This is the bands.xmgr file, which I have plotted in origin. If you are interested, you can plot it in GNU plot also. In origin also, you can plot it up. This is an output file. After doing the exercise, you can also, I think you will also be able to generate this kind of structure. Here, just one thing is that in the bands.out file, if you open it up, you can find the high symmetry points as an X coordinate because it's a 2-column data file. So in the X direction, it will plot the high symmetry points, and in the Y direction, it will plot the energy. Points. This information is given in the bands.out file. So you can open it up and you can read it up, the X coordinate, and according to this coordinate, you can put it this line. This line will not come in the plotting file. This dashed line, you have to put it separately to show the high symmetry points. It's a very easy process. You can generate, you can try different paths to check your band structure is matching with the literature or not. So you can play a lot with this. Next part, I discuss about the density of state calculation. Now, density of state. What is density of state? Now, the band structure, what we have seen, band structure is in a particular direction. Density of state gives you the information of the electronic state in the whole Brillouin zone. So, what you need to do, you need to sample up the Brillouin zone in a more dense KMS. Means what you have done in SCF, like SCF you have done for 6 cross 6 cross 6 KMS, but when you do density of state calculation, you must be at least double of this KMS. Double or triple, you can try with this. At least it should be double. So what we need to do? First, we need to do a SCF calculation. then we need to do a non-self-consistent calculation with dense k-mesh. Next, we need to do a density of state. This is basically DOS is a data point collection. It will give you a data point set from where you can plot the density of state of the sample. So here, one thing to remember is that we need to give the system a more dense k-mesh to calculate the density of state. Now, this is an example files. This is the scf.in and nscf.in. So what I have done from the calculation SCF part, I have given it, made it non-SCF, NSCF calculation, but their prefix and outdeal should be same. One extra term I have added it up, occupation equal to tetrahedra. What this means is that this space sampling should be done uniformly over the whole Brillouin zone. So this part guarantees you that the k-space dividing should be equal, not abrupt. It should give you a smooth case points variation in the Brillouin zone. And one more thing I have changed it up. What I have told earlier, that the k point sampling in the SCF, what I have done for 6 cross 6 cross 6, but in NSCF calculation, I have done it for 12 cross 12 cross 12. I have doubled it up. And in the DOS calculation, just prefix and outdeal are same. I have put a name that DOS.dat. In that DAT file, all the data will be stored, and you need to plot first two columns of the data file to get the density of states. It's also not very complicated. It's also a very easy thing to plot. This DOS.dat file, if you plot it up, it will show like this. Your turn to plot it up and check with the literature. With your optimized lattice constant, cutoff energy, and k-point mesh. Now it's a point, it's just a plotting to have a feeling that density of states and band structure as saying some a bit similar information. Okay, now you can also plot it up. Structure and DOS plotting, the process is same for everyone. You can check with other materials the density of state. Now, just have a not having a black box, I have just want to give you a feeling what is happening inside the computer, how code is trying to do all this calculation. Just I am trying to give you a brief overview in a very simple manner. The code basically, code is trying to solve a many body Schrödinger equation. It is trying to solve, when it's trying to many body Schrödinger equation, it needs a lot of approximation to reach an equation which can be solvable through computation. This is called quantum equation. This is one kind of Schrödinger equation. So here is the part of kinetic energy part. What you know, this is the potential part. This potential is external nuclear potential, heart ray potential. This is the exchange correlation potential. This nuclear potential is arising from the nuclear positions, heart rate potential, which electron is experiencing due to the presence of other electrons. And this exchange correlation potential is the most toughest part for any DFT code to calculate. It is considering what is the effect of correlation of electrons, means what is the interaction of different electrons. So for DFT, the most toughest part is to calculate the exchange correlation function. So what these potential are coming from and how the code is taking care of all these potentials. So when we give an input file, we in the system part, we always try to define what is the structure. From the structural information and from your pseudo potential file, the ionic potential is constructed. So if you don't give the system information, ionic potential will not generate. So the system informations will create an ionic potential with the help of your pseudo potential file. So pseudo potential is very important. Next part is that when you give the information that I need an SCF calculation, means self-consistent field calculation, then from this nuclear position, it will try to guess what is the electron density of the system. So it is the first criteria one system needs to do. So that is the reason for every calculation you need to do an SCF calculation first. So if you guess what is the electron density, then it's bit easier. Then you can compute what is the heart rate potential and what is the exchange correlation potential through Poisson's equation. We know it. And after computing this heart rate and exchange correlation potential, we can add up the total and find the total potential, ionic potential, heart rate potential, and exchange correlation potential. So what I told it earlier, that this pseudo potential file will give you ionic potential, and this PBE functional, it will give you the information how exchange correlation function will work. So correlation function is the toughest part. It is taken care of by the pseudo potential file. So you have to be a bit more careful of choosing this pseudo potential because it is giving you the exchange correlation function. So you can try to change different pseudo potentials, means different exchange correlation function you are taking care of. So the result will be a different. So you need to check also with the pseudo potential how your result is vary. After this total potential is calculated, then the next part is to solve this Schrodinger equation. This is the most expensive part, and this is through diagonalization method. The code is trying to solve what is its energy eigenvalue and what is its wave function. Now, if you are able to solve this equation, then you can find what is the wave function of the system. From the wave function, you can generate again the density. Why to generate? Just we'll look it here. Now you have generated a new density. Now you need to check whether your initial density and newly computed density are within a tolerance level or not. This is called self-consistency. And the tolerance level you are giving through this after in this electron path, not path, in this electron block. Here, the converse threshold you are giving is a value. If the new and the old density are less than this converse value, then you can say system is self-consistent. If it is not, then we need to again compute the new density and compute the Hartree exchange potential. And this is done by utilizing this mixing beta parameter. Mixing beta parameter is giving you that what is the percentage you mix up to get a new density. Means if you say mixing beta is 0.7, then 70% of the new density and 30% of the old density will give you the new potential. And it will give you an iteration. That is why in the self SCF calculation, you found number of iterations. First iteration, second iteration, third iteration. And if you find that after 5 iterations, it is converged, means after 5 iterations, this self-consistent criteria, what we have given it here is satisfied. When it is satisfied, then you are happy. Your code, your job is self-consistent. Now you are able to find what is the energy of the system, what is the force of the system. Okay, Quantum ESPRESSO runs. This is a schematic view. Now, if you were able to calculate the force, I'm just trying, yeah.
ওই সিউডো পোটেনশিয়াল থেকে আয়নিক পোটেনশিয়ালটা বের করব এটা বুঝলাম, কিন্তু ওই হার্ট্রি পোটেনশিয়াল আর এক্সচেঞ্জ কোরিলেশন পোটেনশিয়াল ওটা কিভাবে বের করব আরেকবারটি বলো না।
When you construct ionic potential is differently. When you are able to guess what is the electron density of the system. If you find the electron density, if you are able to guess the electron density, then by using Poisson's equation, you can find the potential. In electrostatics, okay, just I'm showing you. Are you able to see my screen? So,
yes.
Yeah. See this equation.
Poisson's equation.
Density, then you are able to find the Hartree potential. So I will send you also this PDF so that you can found a bit more interesting the way to solve it. It was very interesting to read what is the procedure.
Okay.
So it's clear, I think.
Yes.
Okay. When to find the force, if you find the then you can move the atoms along this force direction what is the direction of the force. Then from the force, can we calculate the optimized structure through force calculation? It's already optimized the structure through total energy calculation. Now, there is a second way to calculating force. What is the optimized structure? Is one way you have done it earlier is the energy calculation. Second way is to do with the force calculation. ESPRESSO has a different calculation procedure known as VC relux. Relux is known as variable scale relux, through which you can find what is the cell parameters, and you can also optimize what is your atomic position. In the total energy calculation, what happens? You are able to find what is the cell parameter, but at that point you are not able to find what is the exact atomic position of the system. So VC relux calculation offers you a very good way to check what is your cell parameter and what is your atomic positions. For this thing, add two different block. One is ion block, one is cell block. You can read it up in the Quantum ESPRESSO pw.x input files, and you can find it up, and you can use parameters according to your requirements. So in this structure optimization, what can be done? Cell parameters can be tuned and coordinates of the atom can be changed by relux calculation. This is also the same pw.x calculation. This is a schematic. This is an output file of the system. So during checking the output file, you have to be very conscious about this line: begin final coordinates. You have to here where it is written. After that, you can find the optimized cell parameters, because it is doing in an iterative way. So there are different cell parameters are written in the output file, but you not need to consider that point where it is written begin final coordinates. So remember this: begin final coordinates. After this, what is the cell parameters it is written, and atomic position it is written. It is the optimized structure for your system. Here I am just showing this is my input parameter was. So you can check it, and you can also check it through energy minimization, and I have also given it in the exercise, so you can do it. Tell me result. Okay, so I'm just giving another flavor of this structure optimization, is that sometimes we are not very interested to change the cell parameters, because sometimes we got it from the experiment. So there is a way not to change the cell parameter, but we can try to optimize what are the atom positions. For this, you run relux calculation, not VC relux. You need to do relux calculation. Your cell parameter will not be changed. It will remain fixed. What will give you? It will give you only the position shifting. So sometimes it is required, and you can find what is the coordinates of the atom after relaxation, and it is the same way with VC relux calculation. So I can say, depending on your requirements, do the structure relaxation. What you need, first understand what you need, then do the structure relaxation, either through VC relax or relax calculations. Okay, that's all for today. Thank you for your attention and enjoy the exercises and have a good time. Be an expert in this field.
Thank you, Arunavada.
Okay.
If anyone have any question, please.
Arunavada,
Yeah. Yes. Just
যখন
Yeah.
তুমি ব্যাংক স্ট্রাকচার দেখছো মনে করো তুমি ডিফারেন্ট কে পয়েন্ট চুজ করলে, এবার এই কে
Yes,
পয়েন্ট চুজ করার কি মানে কোনো অপটিমাইজ মানে ডিফারেন্ট সিস্টেম টু সিস্টেম ডিপেন্ডেন্ট নাকি আমি
what I have told you first, that for doing a band structure calculation, first you need to know what is its Brillouin zone, what the
আওয়াজ আসছে না
আওয়াজ আসেনি।
Okay, are you able to hear you now?
Yes.
Yes. Subhankar, are you able to hear?
হ্যাঁ হ্যাঁ বলেন
Yeah. If you have a structure, then first you need to know what is its Brillouin zone. Okay, first you understand this. Yeah, if you know the Brillouin zone of this system, then you can know what is its high symmetry directions. Along these high symmetry directions, if you can calculate in any direction, no problem, but in high symmetry directions are the most important one.
ওকে গট ইট থ্যাংক ইউ
Yes. You can do your samples, no problem, but first do the Brillouin zone. If you X crystal will give you the Brillouin zone directions to you, no problem with this. Just you have to know what is your structure.
থ্যাংক
That's
ইউ
it. Okay.
Arunavada,
Yes, Saurabh.
I have a question that when you are talking about the mixing of new and old density state.
Yes.
Is it takes if we mix these two system, it takes
Yeah.
less time to convert the system.
Yes. It will take less time. Otherwise, always you have to take new density of state. Then the system doesn't know.
But every time you will get give 70% or 70%, 30% or
No. You can change it up. It's up to you. You can
how do you
Yeah.
guess that how much percentage we will mix?
Okay. You can check it up. It's always recommended to give you between 0.2 to 0.7. It's always recommended.
Okay.
You can give it 0.2, 0.3, 0.4, and you can check what is the time it is taking to optimize the system.
Okay.
To get the convergence of the system.
Okay.
So you can try it. We always try to do it 0.2. If you give it 0.2, it will take much more time. If you beat a higher site, then convergence is very easy to do.
Okay. Thank you.
Okay. Another. Questions, doubts?